Welcome to the AI Frontiers podcast. This episode is titled Robotics Revolution: From Learning to Collaboration, with the subtitle Synthesizing 32 Papers, published on May 26, 2025. Today, the journey centers on the latest advances in robotics and automation, drawing insights from 32 cutting-edge research papers curated from the arXiv preprint server under the Computer Science Robotics category. Throughout this episode, major research themes will be explored, including learning-based control, human-robot interaction, safety, and hardware innovation. Listeners can expect a thorough tour through foundational methodologies and future trends, as well as an examination of seminal works that are shaping the next generation of robotics. Whether you are a robotics researcher, technologist, or an enthusiast of scientific progress, this narrative will provide an in-depth synthesis of the field's current trajectory. This presentation overview will serve as a navigation guide through the robotics frontier. The stage will be set by contextualizing the breakthroughs defining modern robotics. Dominant research themes shaping the field will be outlined, highlighting their influence across academic and industrial landscapes. Key findings and pivotal methodologies will be uncovered, providing clarity on how robotics is advancing in both theory and application. Special attention will be given to 3 influential papers that exemplify technical rigor and transformative potential. Finally, future directions for robotics and the AI synthesis process behind this episode's creation will be highlighted, ensuring a comprehensive understanding of the state and promise of robotics research. The field of computer science. Robotics integrates engineering disciplines, computer science, and artificial intelligence to create intelligent, adaptive, and collaborative robotic systems. The focus extends beyond traditional automation, emphasizing robots that are capable of learning, adapting, and working in partnership with humans and other machines. The impact of robotics is evident across manufacturing, where precision and productivity are enhanced, healthcare, where new surgical and patient care paradigms emerge, logistics, where autonomous systems optimize goods movement, and service sectors, where robots begin to automate delicate or repetitive tasks. Driving this rapid innovation is a highly interdisciplinary research community, uniting medical engineering, electrical engineering, control theory, computer science, and elements of cognitive science. This convergence is propelling robotics forward at an unprecedented pace. The first dominant theme is learning-based robot control and policy adaptation. Modern robots are increasingly enabled to learn complex behaviors directly from data, leveraging reinforcement learning and imitation learning as core techniques. Noteworthy examples include the work of Jiabao Ji and colleagues, who present a framework for grounding large language models in physical constraints, thereby enabling robust, multi-robot control. Another significant contribution is the EgoZero system by Vincent Liu and collaborators, where robots acquire manipulation skills directly from human demonstrations recorded via smart glasses, without any robot-specific data involved. This trend signals a shift toward adaptive generalizable robot policies that can operate across diverse tasks and environments, marking a fundamental evolution in how robot intelligence is developed. The second theme centers on human-robot interaction and communication. As robots transition from controlled laboratory settings to real-world environments, their ability to collaborate physically and communicate naturally with humans becomes paramount. Recent research advances physical collaboration, with Yongxiang Wang and colleagues introducing the Core pipeline, which automatically generates intent-explaining language for robots engaged in assistive tasks. This enhances transparency and trust in human-robot interactions. Fuse Sun and co-authors present an empathetic humanoid tutor that incorporates emotional intelligence, memory, and gestural communication to foster engagement in educational contexts. These developments are enabling robots to become intuitive partners and collaborators, moving beyond the role of mere tools. The third theme involves the integration of foundation models, embodied artificial intelligence, and safety. Foundation models, large pre-trained neural networks capable of processing multiple modalities, are now empowering robots with advanced understanding and reasoning capabilities. Matthew Lysandra and colleagues review how these models are transforming mobile service robots, enabling interpretation of complex instructions and flexible adaptation to new tasks. Safety and risk awareness are also highlighted, with Ran Yu and collaborators developing uncertainty-aware control for autonomous vehicles, and Julio de la Torre Vanegas introducing vision-based risk assessment for safe drone operation. The technical concept of foundation models, defined as large neural networks capable of multimodal learning, is underpinning this transformation by bridging perception, reasoning, and action in robotics. Theme 4 covers motion planning, reactive intelligence, and hardware innovation. Robots now plan and execute safe, adaptive motions in real time, supported by advances in trajectory generation, model predictive control, and tactile sensing. Research by Murooka and colleagues demonstrates how tactile feedback improves robot adaptability in complex environments. Hardware innovation is equally prominent, exemplified by Walid Shaker's development of low-cost surgical painting robots and Wenjing Ren's cooperative aerial systems for payload pickup in cluttered spaces. The technical concept of model predictive control, real-time decision-making based on future predictions, is central to achieving robust and flexible robot behavior in dynamic, real-world settings. A synthesis of key findings across the 32 reviewed papers reveals several pivotal advances. Constraint-aware robot planning, even with relatively small language models, can outperform much larger models in multi-robot control tasks when grounded in physical constraints, as shown by Jiabao Ji and colleagues. Robots are now able to learn directly from human egocentric data, with Vincent Liu's EgoZero system achieving robust zero-shot transfer from human demonstrations to real robotic arms. Masaki Murooka and his team demonstrate that whole-body tactile feedback significantly enhances humanoid robot stability and adaptability. Vision-based risk assessment, as introduced by Julio de la Torre Vanegas, enables robes to generalize from a single demonstrations to used tasks, marking a leap toward SLAMs, and Haben robot Vinamings. A Lazarite by generalize from a single demonstration to new tasks, marking a leap forward in data-efficient robot learning. Contemporary robotics research is propelled by a variety of sophisticated methodologies. Reinforcement learning and reward engineering guide robot actions, enabling autonomous discovery of complex behaviors through structured feedback. Imitation learning leverages human demonstrations for rapid adaptation, reducing dependence on explicit reward design and facilitating transfer to novel tasks. The integration of multimodal foundation models allows robots to interpret and act upon language, vision, and action cues, supporting semantic understanding and transfer learning. Model predictive control provides robust, real-time decision-making by explicitly handling constraints and forecasting future system states. Further, the integration of rich sensing and simulation platforms accelerates safe, scalable development by providing realistic training and evaluation environments, though challenges remain in transferring solutions from simulation to real-world contexts. The first seminal paper, authored by Jiabao Ji and colleagues, is titled Collision and Reachability Aware, Multi-Robot Control with Grounded Large Language Model Planners. This research addresses a fundamental challenge, ensuring that large language models used for robot controls usurate both Sivathant. The authors introduce a framework that grounds language model planning in physical constraints by employing reinforcement learning with verifiable rewards, rebutting the model only when action plans are valid and successful. This approach, known as RLVR, incentivizes the internalization of physical constraints such as collision avoidance and reachability. Evaluations on the BoxNet benchmark and the BOX-NET 3D environment, using both QWEN 2.5-3B.SINSTRUCT and QWEN 3-4B models, demonstrate that grounded models with RLVR robustly outperform larger, unconstrained counterparts. The impact of this work is significant. It enables resource-efficient, scalable robot control in multi-agent environments, showing that awareness of physical constraints is essential for effective real-world deployment of language model planners. The second influential paper, EgoZero, Robot Learning from Smart Glasses, authored by Vincent Liu and collaborators, tackles the bottleneck of acquiring high-quality robot-specific demonstration data. EgoZero enables robots to learn manipulation skills directly from human demonstrations recorded through smart glasses, with no need for robot-specific calibration or teleoperation. The system operates through three components: action extraction from human demonstrations, state compression to create morphology-agnostic representations, and closed-loop policy learning that generalizes across robot morphologies and tasks. Evaluated on a Franca Panda robotic arm across 7 tasks, EgoZero achieves a 70% success rate in zero-shot transfer, meaning robots can perform new tasks after only brief human data collection. This approach democratizes robot learning by leveraging natural human activity, signaling a future where robots can learn from widespread, real-world human experiences and adapt to new environments with unprecedented agility. The third seminal paper, authored by Masaki Murooka and his team, is titled Whole-Body Multi-Contact Motion Control for Humanoid Robots Based on Distributed Tactile Sensors. This work addresses the challenge of enabling humanoid robots to perform robust whole-body motions in complex environments. By integrating distributed deformable tactile sensors across the robot's limbs, the system measures the magnitude and distribution of contact forces, enabling the robot to use any part of its body for support or manipulation. The control framework extends previous multi-contact controllers by incorporating feedback from both traditional force-torque and novel tactile sensors, stabilizing motion in real time. Validation on the RHP Kaleido humanoid robot demonstrates significant improvements in stability and adaptability, particularly during tasks requiring intermediate area contacts. This innovation unlocks new levels of dexterity for humanoids, facilitating deployment in unstructured settings such as disaster response, elder care, and household environments. Looking ahead, several promising directions are emerging for the field of robotics. Scaling up robot learning by harnessing data from wearable and ambient sensors, as exemplified by EgoZero, is anticipated to expand the diversity and realism of training datasets. Advancements in grounding language and vision models within physical constraints will further ensure that robot actions remain safe, reliable, and interpretable. The development of whole-body, multi-contact humanoid interaction capabilities, leveraging distributed tactile sensing and adaptive control, promises enhanced dexterity and robustness. Prioritizing risk assessment and safe exploration in autonomous systems, particularly for safety-critical domains such as aerial robotics and autonomous driving, will remain a central focus. Finally, the ongoing integration of foundation models will enable more natural communication and context-aware adaptation, driving the next era of intelligent, collaborative robots. This AI synthesis and review were created through a rigorous multi-step process. Research analysis was powered by GPT 4.1 from OpenAI, ensuring comprehensive synthesis across the 32 selected papers. Text-to-speech synthesis utilized the DeepGram platform, while visuals accompanying this presentation were generated using Grok. To ensure clarity and technical accuracy, the content underwent expert human review. It should be noted that despite these measures, some oversights may remain. All referenced papers and technical sources are available for independent review, allowing listeners to explore the primary literature in detail. Thank you for exploring the frontiers of robotics with AI Frontiers. To stay updated with the latest breakthroughs in robotics and artificial intelligence, you are encouraged to subscribe to our YouTube channel for new episodes and join a growing community of innovators and enthusiasts. In this podcast, the latest breakthroughs in computer science and AI are brought directly to you, sourced from the arXiv preprint server. From neural networks to quantum computing, complex research is made accessible, ensuring you remain informed and ahead of the curve. Whether you are a developer, researcher, or technology enthusiast, AI Frontiers provides daily insights from the cutting edge of the field. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.